Everyone, so today we're talking about carbohydrate loading and ergogenic aspects. That's chapter 4, part 3. So what is carbohydrate or glycogen loading? Because carbohydrates become increasingly important as a fuel for muscular exercise as the intensity of the exercise increases, and because the amount of carbohydrates stored in the body is limited, muscle and liver glycogen depletion could be factors that limit performance capacity in distance events, characterized by high levels of energy expenditure for prolonged periods. So carbohydrate loading, also called glycogen loading or glycogen supercompensation, is a dietary technique designed to promote a significant increase in the glycogen content in both the liver and in the muscles in an attempt to delay the onset of fatigue. It is generally used for 3 to 7 days in preparation for major athletic competitions. So what type of athlete would benefit from carbohydrate loading? In general, carbohydrate loading is primarily suited for individuals who will sustain high levels of continuous energy expenditure for prolonged periods, such as long-distance runners, swimmers, bicyclists, triathletes, cross-country skiers, and similar athletes. In addition, athletes who are involved in prolonged stop-and-go activities such as soccer, lacrosse, and tournament play sports like tennis and handball may benefit. For example, Rico Sans and others concluded that exhaustion during a soccer-specific performance is related to the capacity to use muscle glycogen, underlying the importance of glycogen loading. In essence, carbohydrate loading may be effective for athletes engaged in events that use muscle glycogen as the major energy source, and that may lead to a depletion of glycogen in the muscle fibers. Athletes who compete in sports involving high-intensity, short-duration energy and expenditure will not benefit from carbohydrate loading. For example, Hatfield and others reported no effects of carbohydrate loading on performance in resistance training involving multiple sets of maximal jump squats. However, bodybuilders have been reported to carbohydrate load in attempts to appear more muscular owing to increased muscle glycogen levels and associated water retention. Recall from chapter 3 that humans have several different types of skeletal muscle fibers. In general, the slow twitch red and fast twitch red fibers are used mainly during long continuous activities and are aerobic in nature, whereas the fast twitch white fibers are used for short, fast activities and are anaerobic in nature. Consider the differences between a distance runner and a soccer player. The former may run at a steady pace for hours, whereas the latter will constantly be changing speeds, with many bouts of full speed interspersed with recovery periods of slower running. Research has shown that glycogen depletion patterns of the two different muscle fiber types are related to the type of exercise. Long, continuous exercise depletes glycogen principally in the slow twitch red and fast twitch red fibers, whereas fast, intermittent bouts of exercise with periods of rest, actually a form of interval training, primarily deplete glycogen in the fast twitch white fibers. However, it should be noted that glycogen depletion may occur in all types of fibers in either prolonged, continuous, or intermittent exercise, and may be quite appreciable depending upon intensity and duration of the exercise bouts. If carbohydrate loading works for the specific muscle fiber involved, then both types of athletes may benefit. Both should have greater glycogen stores in the later stages of their respective athletic contests. So, how do you carbohydrate load? As you might suspect, the key to carbohydrate loading is to switch from the normal but balanced diet to one very high in carbohydrate content. The original classic carbohydrate loading technique emanating from earlier Scandinavian research involved a glycogen depletion stage induced by prolonged exercise and a restricted diet. For example, a runner might go for an 18 to 20 mile run to use as much stored glycogen as possible and then ingest very little carbohydrate in the following 2 to 3 day period. Exercises continue during this 2 to 3 day period to keep glycogen stores low. Following the depletion stage, the loading stage begins. During this phase, carbohydrate may contribute 70 or more % of the caloric intake. The intensity and duration of exercise during this phase were reduced considerably. The usual case was to rest fully for 2 to 3 days. Thus, The classic carbohydrate loading pattern involved 3 stages: depletion, carbohydrate deprivation, so a high-fat protein diet, and carbohydrate loading. However, this original method may be particularly difficult to tolerate, especially if one tries to exercise at high levels during the depletion phase. The lack of carbohydrate in the diet combined with the exercise bouts may elicit symptoms of hypoglycemia. Weakness, lethargy, and irritability would be noted. Moreover, prolonged exhaustive exercise may lead to muscle trauma, which may actually impair the storage of extra glycogen. So, although some early research supported this technique, more recent data suggests that this strict routine may be unnecessary, particularly the total program of depletion. For example, in trained runners, research has shown that simply changing to a very high carbohydrate diet combined with 1 to 2 days of rest or reduced activity levels, so tapering, will effectively increase muscle and liver glycogen. Well-controlled research has revealed that exhaustive running is not necessary to achieve muscle glycogen supercompensation. It appears to be important to continue endurance training or other high-intensity training specific to the sport during the 7 to 14 days prior to competition. Such training will maintain adequate levels of GLUT4 receptors to transfer blood glucose into the muscle cell and of glycogen synthase, the enzyme in the muscle that synthesizes glycogen from glucose. Evidence also suggests that if the total carbohydrate content is consumed over the entire week, in contrast to concentrating it in 2 to 3 days, there will be little difference in the muscle glycogen content between the two techniques. Although there may be a number of variations in the carbohydrate loading protocol, a general recommended format is also presented in Table 4.9. The interested athlete may want to experiment with both techniques and make adjustments through experience. So here you'll see Table 4.9 with different methods for carbohydrate loading. You see the first day of tapering exercise, and then second day you have a mixed diet of moderate carbohydrate, tapering exercise still. Third day, pretty much the same, and fourth day. The fifth day, you're going to have a high carbohydrate diet with still tapering exercise. And then the sixth day, same high carbohydrate diet. You can either taper exercise or rest. And then seventh day, the same. Eighth day would be your competition. So all of this would begin a week prior to your competition. Your high carbohydrate diet would be about 400 to 800 grams per day, depending on body weight, and about 70 to 80% of dietary calories should be carbohydrate. Here, looking at the daily food plan for carbohydrate loading, although some early research supported this technique, more recent data suggests that this strict routine may be unnecessary, particularly the total program of depletion. Although there may be a number of variations in the carbohydrate loading protocol, a generally recommended format is also presented. So will carbohydrate loading increase muscle glycogen concentration? Most but not all studies show that an appropriate carbohydrate loading protocol compared to normal or low dietary carbohydrate intake will substantially increase muscle glycogen levels. Although some previous research found that muscle glycogen levels in the early phases of loading did not increase as much as in females as in males. More recent, better controlled research by James Paul and Tarnopolsky with their associates revealed that carbohydrate loading increased muscle glycogen concentration in both men and women, provided that total energy intake was adequate. No gender differences were noted. McClay and others noted that women generally have lower resting muscle glycogen levels during the mid-follicular phase of the menstrual cycle as compared to the mid-luteal phase. But the lower glycogen storage in the mid-follicular phase could be overcome by carbohydrate loading. In general, carbohydrate intakes of 8 grams or more per kilogram body weight will provide optimal muscle glycogen concentrations for both males and females. Glycogen content in the muscle has been reported to increase about 2 to 3 times beyond normal, and liver glycogen content nearly doubled following a carbohydrate loading regimen, and this increase may last at least 3 days in a rested athlete. However, it may be important to taper and rest about 2 days prior to the event. So how do I know if my muscles have increased their glycogen stores? You'll start to see, of course, monitoring changes in your body weight. The most accurate way would be, of course, to have a muscle biopsy taken. A needle is inserted into the muscle and a small portion is extracted and analyzed. But this is not very practical. So a practical method that has been recommended is to monitor your changes in body weight. Kreutzmann and others noted that glycogen is stored in the liver, the muscles, and fat cells in hydrated form, 3 to 4 parts water. And so weight gain may occur with carbohydrate loading. Thus, keeping an accurate record of your body weight, which should be recorded every morning as you rise and after you urinate, may help you determine the answer to this question. Approximately 3 grams of water are bound to each gram of stored glycogen. If your body stores an additional 300 to 400 grams of glycogen along with 900 to 1200 grams of water, your body weight will increase about 1200 to 1600 grams, or you'll see about a 2.5 to 3.5 pound change above your normal training weight during the loading phase. The weight gain should be greater with additional glycogen storage. This is indicative that the carbohydrate loading has been effective because rapid weight gains from one day to another are usually due to changes in body water content. So will carbohydrate loading improve exercise performance? Although athletes in most sports may benefit from an increased carbohydrate content in the diet, the full procedure of carbohydrate loading is not necessary for the vast majority of athletes. In general, carbohydrate loading has not been found to enhance performance in single high-intensity exercise tasks ranging up to 60 minutes or so. For example, Vandenberg and others found no effect of muscle glycogen levels manipulated by carbohydrate loading on muscle glycolytic rate during very high-intensity exercise of 125% VO2 max, or an all-out performance at this exercise intensity, a time approximating about 3 minutes. Various other studies have reported that carbohydrate loading does not increase the speed of runners in events ranging from 10 kilometers to the half marathon or in cycling time trials up to 60 minutes. However, Pizza and others using an exercise task consisting of a 15-minute submaximal run followed by a run to exhaustion at 100% VO2 reported an increase in performance associated with carbohydrate loading. The run to exhaustion approximated 5 minutes. In general, this finding is an exception to the rule, so additional research is warranted. Carbohydrate loading may benefit athletes involved in prolonged, intermittent, high-intensity exercise tasks. Carbohydrate loading has been studied most extensively as a means to improve performance in a more prolonged aerobic endurance exercise tasks. In general, the results are supportive of an ergogenic effect. Are there any possible detrimental effects relative to carbohydrate loading? From a performance standpoint, the extra body weight associated with the increased water content may be a disadvantage. In activities where moving the body weight is important, extra energy will be required to lift the extra 2 to 3 pounds of body water. However, in most performance events for which carbohydrate loading is advocated, the benefits from the energy aspects of the increased glycogen should more than offset the additional water weight. Moreover, if the individual is performing in a hot environment with the extra water, even small amounts could be available as a source of sweat and may be helpful in controlling body temperature during exercise in the heat, although one study suggested that the water stored with glycogen did not confer any advantage in regulation of body temperature while exercising in heat. The duration of the exercise, only 45 minutes, would not be sufficient to benefit from the increased water levels. From a health standpoint, there may be hazards to individuals with certain conditions. Although diabetics have been known to carbohydrate load, they should consult their physicians prior to using the technique. Individuals with high blood lipid or cholesterol levels might avoid the high-fat, high-protein diet phase of the depletion phase, if for some reason they prefer the original classic method of carbohydrate loading. Blood serum lipids and cholesterol have been reported to rise significantly during this phase. In addition, these individuals should eat mostly low glycemic index carbohydrates during the loading phase, because an increased intake of high glycemic index carbohydrates may raise blood lipid levels. Furthermore, hypoglycemia may occur during the high-fat protein phase. So if we look at carbohydrates as ergogenic, Throughout this chapter, you have learned that carbohydrate intake in a variety of ways may be used to enhance physical performance. Truly, carbohydrates represent one or of our more important ergogenic nutrients. In this brief section, we shall look at several forms of carbohydrate that might possess ergogenic properties. Additionally, numerous carbohydrate-based products, such as the sports energy drinks, have been marketed to athletes, and many contain purported ergogenic substances such as caffeine, ephedrine, and amino acids. These specific nutritional ergogenics will be discussed in later chapters where appropriate. So pyruvate, the metabolic byproducts of carbohydrate exert an ergogenic effect? Recall that the primary mechanism in the transformation of muscle glycogen into energy is glycolysis. The end product during aerobic metabolism is normally pyruvate. However, glycolysis leading to the formation of pyruvate involves production of a number of metabolic byproducts in a chain of about a dozen sequential steps, each step being controlled by an enzyme. One theory of fatigue is that if one of these steps is blocked by inactivation of an enzyme, glycolysis may not continue at an optimal rate. Since a necessary metabolic byproduct may be in short supply, this blocked step could represent a weak link in the chain, possibly reducing the formation of pyruvate and subsequent ATP production. Pyruvate has been studied as a potential ergogenic aid, as have other metabolic byproducts of carbohydrate metabolism. So pyruvate is a 3-carbon metabolic byproduct of glycolysis. Although the mechanism of its underlying potential as an ergogenic aid is unknown, pyruvate is theorized to accelerate the Krebs cycle or use glucose more efficiently, both of which could enhance exercise performance. DHAP is a combination of pyruvate and dihydroxyacetone, another 3-carbon metabolic byproduct of glycolysis. Pyruvate administered alone has been used in attempts to decrease fat and increase muscle mass, possibly by speeding up Krebs cycle activity. Common and others also reported a significant decrease in body weight and fat mass in healthy overweight men and women following 6 weeks of pyruvate supplementation of about 6 grams per day. Although these findings may be important to the obese, they may not be applicable to the healthy, non-obese, well-trained individual as a means of shedding additional body fat for sports. If we look at DHAP, previous studies with animals have shown that DHAP increases muscle glycogen content. So Ronald Stanko and his associates at the University of Pittsburgh investigated the potential ergogenic effect of DHAP in humans. 2 studies were conducted, both using untrained males as subjects. The dosage of DHAP in both studies was 100 grams per day for 7 days. DHAP was prepared in a 3-to-1 ratio of dihydroxyacetone of 75 grams to sodium pyruvate 25 grams and administered either in jello or artificially sweetened fluids. The placebo in both studies was 100 grams of polykose, a carbohydrate. The DHAP or polykose was substituted for a portion of the carbohydrate in the diet. Both studies were well designed using a double-blind, placebo, repeated measures, crossover approach. In the first study, the diet was standardized at 55% carbohydrate of the daily caloric intake. The criterion test was an arm ergometer exercise task to exhaustion at 60% VO2 peak following a week of supplementation. DHAP significantly increased endurance time, attributed primarily to an increased muscle glycogen concentration and increased extraction of blood glucose, both factors providing more glucose to the exercising muscle. In the second experiment, subjects consumed a high carbohydrate diet of about 70% of the daily caloric intake. The criterion test was a cycle ergometer exercise task to exhaustion at 70% VO2 max. DHAP improved performance in an identical fashion to the first study, the effect being attributed to the increased blood glucose extraction by the exercising muscle. The results of these well-controlled increase muscle mass, possibly by speeding up the Krebs cycle activity. Common and others also reported a decrease in body fat mass. studies indicate an ergogenic effect of DHAP with untrained subjects, but confirming data are needed with well-trained athletes. Lactate salts. As noted previously, lactic acid is a metabolic byproduct of anaerobic glycolysis. We also indicated that although lactic acid is often associated with fatigue, most sports scientists theorize it is the hydrogen ion release that increases the acidity and impairs performance, not the lactate itself. Lactate is actually a small metabolite of glucose. Its formula is three carbon ions, 5 hydrogen carbon ions, and 3 oxygen ions, about half of that of glucose. Thus, lactate still possesses considerable energy and may be converted back to pyruvate to enter the energy pathway into the skeletal muscles. Lactate also may be converted back to glucose by the liver. Various lactate supplements have been studied as a means to enhance endurance performance. For example, Cytomax is a sports drink that contains lactate in a patented form, alpha-L polylactate. Cytomax also contains fructose glucose and a glucose polymer. Ribose is a 5-carbon monosaccharide found throughout body cells as part of various compounds such as RNA or ribonucleic acid and the cell nucleus. Ribose also comprises the sugar portion of adenosine, the nucleotide found in ATP or adenosine triphosphate. ATP, as you recall, is the immediate source of energy for muscle contraction, both in the heart and in skeletal muscles. Although found in nature, very little ribose is consumed in a natural diet. Instead, a specific metabolic pathway, pentose phosphate pathway, produces ribose from glucose to meet our body needs. Recently, ribose supplements made from corn sugar have been marketed to physically active individuals as a means to promote faster recovery in heart and skeletal muscles, presumably by facilitating the formation of adenosine, one of the major components of ATP. Research indicates that strenuous exercise may necessitate rapid recovery of adenosine with muscle cells, which might benefit from adequate ribose. The effect of other supplementation has been evaluated using healthy physically active individuals and athletes. Several studies used an acute supplementation protocol, and others reported 3 grams of ribose provided to moderately trained male cyclists about 25 minutes prior to exercise had no effect, or 5 maximal 30-second anaerobic capacity cycling tests with a 3-minute recovery. In a crossover study, Peveler and others also found no effect of an acute 625 milligram dose of ribose on peak power, mean power, or rate of fatigue in 3 intermittent 30-second Wingate tests of anaerobic capacity in healthy males. Research using chronic supplementation of ribose also does not support an ergogenic effect. Berardi and Ziegenfuss studied the effect of oral ribose supplementation, 32 grams over a 36-hour period, on high-intensity intermittent anaerobic cycle ergometer performance. The exercise task consisted of 6 10-second sprints with a 60-second recovery. They concluded that ribose supplementation does not have a consistent or substantial effect on anaerobic cycle sprinting, as evaluated by peak and mean power output. Helston and others reported that 3 days of ribose supplementation based on body weight, approximately 45 grams daily, elicited a greater resynthesis of ATP compared to the placebo. However, the slight increase in ATP availability did not enhance performance, as there were no differences between the placebo and ribose supplement for mean and peak power outputs. The authors noted that a small reduction in muscle ATP does not appear to limit high-intensity exercise performance. So current data does not necessarily support ergogenic effect of ribose supplementation. If we look at multiple carbohydrate byproducts, sports supplements manufacturers often combine multiple nutrients in a single supplement on the theory that each may exhibit an ergogenic effect, but the effect will be amplified with multiple components. Limited research is available with multiple byproducts of carbohydrate metabolism, but Brown and others investigated the ergogenic potential of a multi-nutrient supplement composed primarily of intermediates of the Krebs cycle, which may be derived from carbohydrate, fat, or protein. 3 weeks of supplementation did not improve cycling time to exhaustion at approximately 70 to 75% of VO2 max, nor did it improve the rate of recovery. So there's limited research, but no beneficial effects on exercise performance or recovery that's been noted. So key aspects of carbohydrate loading is it is not a technique for all types of athletes, but it may benefit athletes involved in long distance competitions such as marathoning. And various carbohydrate loading techniques may be effective to increase muscle glycogen stores, but tapering exercise or rest and a high carbohydrate diet are essential to your training. And then metabolic byproducts of carbohydrate metabolism have been tested as ergogenics, but most have been found to be ineffective, although research with physically trained individuals is limited with several purported ergogenic products. All right, guys, so this finishes up. It's still Chapter 4, Part 3. We'll be talking more about Chapter 4, or finishing up Chapter 4 and looking at the health benefits of carbohydrates later. All right, talk to you soon.